Exciting stuff happening this week. We thought it was already going to happen at this point, but fingers crossed that the Artemis 1 rocket will launch uncrewed this time for our return to the moon, and eventually, of course, humanity's return to the moon for the first time by the time it happens in more than 50 years. And I am grateful to be joined by somebody who is responsible for a key component of the Space Launch System, also known as the SLS, and that's Joe Cassady, Aerojet Rocketdyne's Executive Director of Space. Joe, thanks for joining us. Really appreciate that.
Yeah, great to be here.
Thank you. We're going to specifically talk about Aerojet Rocketdyne's RS-25 engines, which have a pretty rich history that goes way back. So I'm hoping you can sort of just give me a brief update, a fill-in on where those RS-25s got their start.
Sure. Well, yeah, as you say, the RS-25 was also known for many years as the Space Shuttle main engine, and flew on the orbiters. When the orbiters were, retired and we're going to go to museums, we didn't want to waste those engines, so we took them off the tail of the orbiters. And the four engines that are going to fly on Artemis 1 are all shuttle veterans. They've flown on many different flights. I can't remember off the top of my head exactly every flight, but I think it's something like 20 flights they have under their belts already, including I think one of the engines actually was on the flight that returned John Glenn to flight after his many years since his orbital flight when he got to fly on the shuttle. Another little trivia piece that's kind of neat is all four of the engines that are going to be on this flight have a small piece of one of the STS-1 engines. STS-1 was the first shuttle flight. So somewhere in each of the engines, and one of them even has like the igniter, is a heritage part that goes back to STS-1. So we're going all the way back to the very first flight of the shuttle with the engines connecting to the first flight of SLS.
Okay, so now I'm going to test my memory. STS-1, I believe, was crewed only by Robert Crippen and John Young, if there was a program John Young was not involved in, aside from Mercury, because he was a little too young for that, it would honestly be surprising, because he did Gemini, he did Skylab, he did the first space shuttle flight. So that really is, you're talking about a huge piece of space history. And before we started, you referred to yourself as a nerd. I'm a card carrying member of that club when it comes to the space program. So yeah, no, absolutely thrilled to see that. So I want to of course back you up, because these are used engines. Some of the parts are relatively older, but it sounds like because they're reusable, it's really not so much of a concern, like versus a car with 200,000 miles on it.
Right. Yeah, no, not at all. Yeah, these things are super resilient engines, in addition to being high performers. And I think the fact that they have all that heritage was part of why NASA wanted to go this route. These are proven, and there's no doubt that they're going to do the job that we need them to do to get SLS up to orbit.
Okay, so let's talk about that, because as I understand it, there are 4 of them as opposed to 3 on the backs of the shuttles, and they are, I believe, at the base of the main tank there.
We call it the core stage. Yeah,
the core stage. Okay, I'm glad you straightened me out on my terminology there too, Joe. How much of a role do they play in terms of getting Artemis off the ground?
Yeah, so each engine produces about 500,000 pounds of thrust. And so with the 4 of them, that's roughly 2 million pounds of thrust. And then just like on the shuttle, we have the solid rocket boosters, 2 of them, and they contribute about another 6 million pounds of thrust at liftoff, 6 to 6.5. So we're right at 8.5 to 9 million pounds of thrust. It's a change when we take off and lift off the pad. The difference between us and the solids are there to get that initial thrust. They're done in about 2 minutes. We are the sustainer, so we burn for the full 8 minutes to orbit. And so our 2 million pounds of thrust, if you will, is continuous all the way up till we get to orbital velocity. And then the core stage mission is done.
That's absolutely amazing to me that we can go from the ground to orbit in 8 minutes. Yeah. I mean, that's a spectacular feat of engineering.
Yes, 0 to 17,500 miles an hour in 8 minutes. Pretty good acceleration.
Oh my goodness. So what did it take to get these engines from the shuttles and ready them for the SLS job?
Yeah, so obviously it's a different vehicle. One of the big changes is the brains, or the controller that actually, you know, tells the engine what conditions to run at. And I talked about the thrust levels. We vary that thrust level throughout the flight profile for different reasons. You probably heard and remember from the shuttle days, rockets as they're taking off go through what's called max Q, maximum aerodynamic pressure. And that's one thing we want to, you know, keep the thrust down a little bit so we get through that and we break the sound barrier, and then we can throttle up. And so we're actually running these engines at, I believe, 113% is what we've maxed out at so far. So back to the old, you know, standard thrust level that they were supposed to operate at for the shuttle program. We're actually well beyond that. The computer is there to control that flight profile. So that's an updated thing from the shuttle days. The other thing we're doing, we're flying out these veteran shuttle engines now. They'll fly on the first 4 flights of SLS. After that, we're actually now manufacturing new RS-25s. And one of the things we're doing there is taking advantage of the technology we have available today for manufacturing that we didn't have back in the 70s when we built those shuttle engines, things like 3D printing. So we're going to be, building big parts of those engines using that new technology, and that's going to get us more affordability for the program by doing that without sacrificing performance or reliability.
But even still, as we work with these, that main piece is recovered, and those engines can then be reused, whether they're the older ones or the newer ones, right?
No. In this case with SLS, the thing with the whole mission here, going back to the moon, is all about getting more stuff out to the moon than we did with Apollo and staying longer. So what we're doing with this vehicle is we're totally optimizing for performance. So instead of, like you see other vehicles that are reusable now, those are only going to about 200 miles. You know, space station orbits over us about 200 miles up. Anything in Earth orbit is a shorter putt than going to the moon. We're going to 238,000 miles with this vehicle, and we're taking up payloads that are at least 3 times bigger than what any commercial rocket can. So we've really optimized everything toward performance, so we're not recovering any of this. So that's why, again, when I was saying that about the additive manufacturing and 3D printing, one of our big challenges is take these beautiful engines that were so resilient, so reliable, and find out ways to manufacture them so they'll be more affordable. And that's really where we're headed with the program.
Now, that is something you've just educated me. I didn't realize that whole thing is going with the Orion capsule to get it to the moon, and then that's where they part ways. Am I right?
So actually, the core stage will part ways a little sooner. It gets us up to orbital velocity, and then it drops off. We have an upper stage called the Interim Cryogenic Propulsion Stage, or ICPS, and that stays with Orion a little longer. It goes around Earth one time with Orion. They're checking out all the Orion systems at that point, making sure everything looks good. If all is well and it looks like we have a green light to proceed with the mission, we'll fire the RL-10 engine, which is another engine that we provide for the vehicle. And that single RL-10 will do what's called the translunar injection burn, and that'll put it on its way to the moon. And then at that point, its mission is done, and we've expended all the propellant out of it. So it drops away from Orion, and then Orion has a service module that has say a whole complement of engines on it. The main one being the Orion main engine. And that's kind of an interesting story, because if you remember on the shuttle orbiters, there were the 3 RS-25s or SSMEs on the back, but there were also 2 smaller engines just above it, kind of right below the tail. And those were called the orbital maneuvering engines, or OMEs. Those were the engines that were used to bring the orbiters home, because obviously they didn't have the external tank anymore. They had no fuel source for those SSMEs, so they couldn't fire them. They had those other engines on there, and they're a smaller class engine, about, you know, roughly 5,000-pound class engine using space storable propellants. And that's what Orion now is flying for its main engine. And we didn't even have to change the acronym, because now it's the Orion main engine, so it's still the OME. We love reusing acronyms.
That makes it easier to understand.
Easier to remember.
Yeah, oh, agreed. So I neglected to ask you, are we still building the RS-25s in El Segundo?
In Canoga Park, yeah, it's in
Okay.
Los Angeles. Yeah, so yeah, it's our main plant there for the RS-25s. We actually assemble them at Stennis Space Center in Mississippi. So we have an assembly facility down there. And the reason we do that is every one of these engines, before we fly it, we test it. And the big test stands for those, you know, 500,000-pound engines are located down there at NASA Stennis. So we put them together, we put them on the test stand, we fire them up. It's a beautiful thing to go down there and watch it, because we make our own rain. With the hydrogen and oxygen engines, one of the cleanest engines in the world. You know, people talk about green, environmentally friendly. When we burn hydrogen and oxygen together, all we produce is superheated water vapor. So we make big clouds when we test the engine down there in Mississippi.
Well, and that's always amazing to me that 2 basic elements can be put together to do such an incredible thing. Now, I want to make sure I ask you, and I don't know how much you can tell me, and, you know, if you're limited, that's okay. But based on what we saw on Monday, I know we heard the term, you know, engine bleed, and then, you know, some possible cooling issues. What can you tell me about what happened Monday that ended up leading to the scrub?
Yeah, so basically what happened on Monday, we were running a little different profile. Oops, did we freeze up? Oh, do you want me to start that again?
No, I'm still here. You go ahead.
You're still hearing me? Okay, okay. So we run a little different profile for what we call the engine chill-in, and that was where we started to see a sensor on engine 3 was giving us a reading that was higher than what we would normally want to see. So we went through a bunch of different processes to see if that was basically real or not. And in the process of doing that, and subsequent to that, between Monday and now, the team has been looking at a lot of secondary data that we have on the engine. And basically what that's showing us is we should be getting cold enough. All the engines are showing about the same data, the same secondary data. The one thing that's standing out as different is that sensor on engine 3. And it's not really even on the engine. It's up in the core stage where that sensor is located, at the base of the core stage. The bleed part, and what that refers to, is simply that we're bringing that hydrogen in to the upper part of the engine. It's cooling the engine, and then it sort of turns to gas because it's liquid hydrogen at minus 423. As it takes heat out of the engine, it turns to gas. We have to get that gas out. So we have a valve that leads that gas out. Just sort of like if you worked on your brakes on your car ever, you know, when you do your brakes, you have to have that little bleed to get the air out of the lines. And that's essentially what we're doing there. And that hydrogen goes out through a flare stack. If you watch the launch videos and stuff, you'll see off on the side of the pad, there's this little flame burning over there. And that's what that is. That's the hydrogen flare stack burning off that hydrogen that's coming out as we're chilling the engines in.
Okay,
So
so not a signal that you've elected a new pope. Good to know.
yeah, that's right, exactly. And we've changed that procedure now to start sooner and let us run that a little longer. And looking again at this other data besides the sensor, we're pretty confident that we really are getting cold. And what that's telling us is that's probably just a problem with the sensor, not a real problem.
That's good to know. So I think that begs the question, does it mean we're looking better for Saturday's window?
We're feeling pretty good about Saturday right now. The only thing I guess I'm a little leery of is the Florida weather. So we're hoping for the best there.
Excellent. And, before we wrap up, I can only imagine that after years of working on the shuttles with these engines, that this is a particular point of pride that such a huge next step involves Aerojet products.
Yes, there there are employees in all corners of the country, and that's us and our suppliers. We have suppliers all across the United States. There are Aerojet Rocketdyne employees right there in the Seattle area who have propulsion devices on Orion. That's our payload on this launch. That's the whole reason we're doing the launch, is to take Orion out to the moon and bring it home safely. So we're ready for crew on Artemis 2. So all across the country, every one of those folks are watching this, and you can bet there's a ton of pride in seeing this go off successfully.
Well, I think it's wonderful, and I know I'm going to feel pretty proud. I'm just glad I don't have to get up at 5:30 in the morning for Saturday's launch. I still get to sleep in a little bit, but that is terrific. And in the meantime, of course, we appreciate you joining us. Joe Cassady, Aerojet Rocketdyne's Executive Director of Space. Thanks, Joe. Appreciate you taking the time.
Sure. Thanks, Ryan.